For my second performance today, I will be giving you a little deeper dive into the storage systems at OLCF. There will be no singing and dancing. I gave that up 20 years ago. So, overview and goals for this lecture. So I'll give you a quick background on NCCS, which is a large organization, and OLCF's approach to HPC storage. Then we'll go into a high-level overview of our current center-wide shared storage file system called Alpine. And then I'll give a little bit more deep dive on Orion, which is the next big thing. So overview of HPC storage at NCCS and OLCF. So NCCS, National Center for Computational Sciences, is actually a pretty big deal at ORNL. Most people have heard about OLCF. It's the leadership computing facility. But, you know, this is OLCF, and this is OLCF. Everything else here supports other programs, particular DOE programs. So we support OSCAR, which is Advanced Scientific Computing Research. That's the OLCF and DOE in general. We also support NOAA, the National Climate Research Center, and the Air Force for climate modeling. We have OpenStack resources for doing cloud-like things for ONRL researchers, which is CADES, the Compute and Data Environment for Science. We have various test beds. We even do some work in scalable protected infrastructure. So think about HIPAA or protected health information. We have an entire separate enclave for handling data that has enhanced controls for privacy, for example. As you see in this picture, so each one of these square rectangles is a system. Like, it could be an HPC system, it could be a cluster, it could just be like login or data transfer nodes. So DTN stands for data transfer nodes. So each one, we have a bunch of systems, and then the things that look like disks in this picture are the storage systems that are associated with all of these systems. And as you can see in one of these colored boxes, we typically have a bunch of systems and then some set of shared storage systems. Now, when it comes to storage, so this gets into lifetime and performance. So for OLCF, you know, we have job terms. So this is the node local storage, 24 hours or less storage that's available in Summit and will be available in Frontier. And then the short term, which is Scratch, essentially. So we have Alpine, ARCs, and Wolf file systems. So for those of you who are playing with Ascent, I believe you are accessing Wolf. Wolf also supports I think that's biological and environment research, but I could be wrong. And then we have specific file systems for Air Force and climate folks, NOAA. And so that's relatively short term, and that's all fast storage, or at least fast-ish. And then you basically get down to if you're not, if you want to keep your data around longer, then you need to move it over into our archive systems, like HPSS. And we don't actually provide long-term data storage for some of the programs. So here's a short listing of some of our Scratch file systems for the various users. So the big one here is Alpine, which I will talk about a little bit more. But you can see these range in size. So the capacity is, you know, from small number of petabytes, larger number of petabytes, really big, large number of petabytes. And again, these bandwidth numbers here, as Phil mentioned earlier, these are hero numbers. This is data that was collected when the first system is first stood up, and we have everybody silent on the system, and we do hero efforts to figure out what's the best we can do. So yeah, 2.5 terabytes per second on Alpine. That's great, but who sees it? This is some of our archive systems. Just to, again, hundreds of petabytes. Not great performance. So let's talk about Alpine, the current center-wide shared file system. So first, if you haven't heard this terminology before, center-wide, I'm going to describe why OLCF chooses to deploy center-wide shared file systems. Then we'll go into some of the details of Alpine itself. So historically, this is 15-ish years ago, when you bought a supercomputer, it came with a tightly coupled storage system. Vendors like this because they could sell you more stuff. But this also has several drawbacks. So one is vendors like it because its storage is expensive. It can actually be up to the third of a cost of a large-scale HPC resource. If you have a storage system that's associated with every HPC system you deploy, that means you're creating a lot of work for your administrators and a lot of work for your users to figure out, what file storage system should I be using with this compute platform. It also increases the amount of large-scale data movement you have to perform. So if I can only access data from the tightly coupled HPC system, then what if I need different resources to analyze the data I produced on the compute? And I'm going to involve taking my simulation results, which may be large, and transferring them to another storage system just so I can analyze them. Data movement also equals power consumption. Facilities have limited power budgets. And finally, when you tight couple storage to HPC compute, that often also leads to situations where if the compute is down, your storage is also down. And people like the ability to access their data even if they can't actually compute on it at the time. So a while back, some smart people in OLCF came up with the Spider architecture for center-wide shared file systems. So this is my best graphical representation on the right here. So imagine a very, very large spider where data sits in its body. And all the legs stretch out to all the compute resources. And so this is just, everybody sharing the same storage. They'll all have the same access. And in reality, the sizes of these legs are actually different. So the legs represent the bandwidth you provide to the different HPC compute systems. And then for a particular compute system, the image here on the left, this is generally what it looks like. You have compute nodes, again, you've seen this picture before, talking to I/O nodes. And then we go into the I/O network, which we call the Spider I/O network, or Scion. And it consists of a bunch of switches that are all connected to each other and to many systems. And then those switches give you access to the I/O servers, which manage boatloads of storage. Boatloads. All right, Spider through the years. So it started back with Spider 1 in 2008. This was helping us deploy Lustre with Jaguar. Most of you probably have not used Jaguar. I have. So this was during my PhD that I worked on Jaguar. When I went to Oak Ridge in 2012 was when we were deploying Titan. And so Spider 1 was a Lustre file system, 10 petabytes in total capacity, some unknown number of disks. But so Jaguar and Titan are interesting because so Jaguar was 18,000 nodes. Titan was 18,000 nodes, and that's because we repurposed the cabinets. We basically took out the insides of every Jaguar cabinet and replaced it with Titan insides, put a new label on it. The hero number for Spider 1 was, at the time, it was very good. It was 240 gigabytes per second. About 5 years later, tripled the capacity and did 5 times the amount of hero bandwidth, using 20,000 disks for that capacity. Again, this was Lustre, so we have a lot of Lustre experience at OLCF. We actually have somebody who works for ORNL who contributes more lines to the Lustre source code than any other vendor, which is interesting. And then roughly 5 years later, we deployed Spider 3, which is now based on Spectrum scale, GPFS, and supports primarily Summit, which is in production, and Frontier, which is undergoing acceptance testing. You can see that the number of clients has relatively drastically gone down. That's because, Jaguar Titan days, well, Jaguar specifically, was all CPU-based compute. So we had lots and lots of nodes with lots of cores. Titan was the first move to a GPU and accelerated architecture. So we had 1 GPU per node per 18,000 nodes. Summit gave you 6 GPUs per node. Frontier gives you 8 GPUs per node, logically. So we've actually reduced the number of nodes. So Summit has roughly 4,600 nodes. Frontier will have over 9,000 nodes. So we reduced the number of clients, which is good for the parallel file system perspective, and increased the capacity and the bandwidth. So, Alpine. It's very, very pretty. Those are just racks of essentially racks and racks of storage drives. So we have 250 petabytes of usable capacity. So the key thing here from a user standpoint is 2 numbers. So this is all assumes that you do nice I/O 16 megabyte blocks. 16 megabytes can often be a lot of application data. It could be a significant portion of a matrix or a mesh. And the other thing here is this minimum fragment, 16 kilobytes. So basically anything you want to store that's less than 16 kilobytes will still use up 16 kilobytes of space. So if you have an application out there that's doing, 4 kilobyte writes, you're losing 75% of your storage capacity. The hero numbers, again, 2.5 terabytes for sequential read and write, 2.2 for random. So this, GPFS is actually kind of nice. Intuitively makes all the accesses random on its own, and so you don't see much of a drop when you go from sequential to random as far as here numbers go. And you can push it. You can do 2.6 million I/O operations per second for small files. So declustered RAID with dual parity. Most of you don't need to know what that means, but generally it just means we have disks in the system that keep parity, which is recovery information for the actual data. And the way it's set up is made it so that failures in one storage domain don't affect others. And so it makes it easier to rebuild after failures. What's this look like? An elastic storage server, an ESS, is it's a piece of hardware that you can buy from IBM. The GL4 is the product name. We have 77 of these things. Each one has 2 Power 9 CPUs, so it's not exactly the same Power 9 CPU that's in a Summit node, but and then a total of 4 InfiniBand connections to the storage I/O network for a total of 100 gigabyte per second access from an ESS. And this is all managing a pool of 32,000, almost 32,500, 10 terabyte drives. So these are spinning disk drives. And then the figure here on the right is kind of a zoomed in portion of the top-down layout of Summit. So over here we have these are all compute racks, and then we have the data racks here. This is easier to see in this picture. So we have a nice 3D model of the first floor data center. This picture is a little outdated because Titan's still sitting here. So this is Summit, Compute, and this is Alpine. And this is a pretty big room, actually. So it takes up a significant portion of floor space. I don't have an updated picture. I'll just say that all this space here now is Frontier. All right, so we had some numbers in our contractual specification for buying Spider 3 that worried the vendors a little bit. So first of all, we wanted a single GPFS file system, so one namespace to include all of the capacity. Early on in the process, they're like, oh, we can give you 6 namespaces. We're like, no. They made it work. Previous systems had problems with large number of files in a single directory. This becomes important when you're doing parallel applications with file per process. You can now do 10 million files in a single directory, and GPFS will actually, not fall over. It's configured to support a file size that you aggregate all the system memory in Summit, and you can have a file of that size. We bumped up its ability to process metadata to up to 50,000 operations per second for a single directory. We did some performance improvements to the internal communication inside GPFS, and then lots of improvements to how we monitor such a large storage system using techniques from cloud space and big data analysis. So that's an overview of where we are with the current center-wide shared file system. So now I'd like to talk about the fun stuff, which is the next one, Orion. So we'll talk about its architecture, the architecture and features of Lustre on which Orion is based, and then I'll give you some details about Orion itself. So here's a little bit of a deep dive on the architecture of Lustre in particular. I'm reusing the graphic, and I'm just providing more detail. So again, it's a parallel file system, so it tends to separate data storage and metadata servers. And so in Lustre, your I/O servers are now known as object storage servers because objects are the base data storage format. And the metadata servers are known as MDS. So OSSs and MDSs have storage associated with them. In the case of object storage servers, they have object storage targets, and these are typically spinning disks. They don't have to be spinning disks. And in the case of metadata servers, they have metadata targets, which are typically flash-based. Do a good job for directory trees and metadata, quick metadata access. So clients, as I mentioned this in the previous talk, but when you do an access, you'll talk to a metadata server first to either navigate your file system or retrieve your statistics about a particular file, such as its size or access permissions. And then the metadata service also tracks where throughout the system file extents are located. And then when you actually want to read or write data, you go directly over the network to talk to the object storage servers to do those reads and writes using a predefined network size of 1 megabyte, regardless of how you're actually structuring your I/O. So some terminology, and we hinted at this earlier. So striping is important in Lustre. So there's 2 factors that most users will eventually hear about or have to incorporate. So the Lustre stripe size, this is the size of data objects used by object storage servers to spread data across OSTs, and they do this in a round-robin fashion. And then there's the Lustre stripe width, which is size versus width. This is always something that's a poor choice of. Width is a number of OSTs that you stripe across. To me, size and width are very similar concepts, and I think they should have chose something different for width. But as an example, assume you have a 1 gigabyte file and your stripe size is a megabyte, which is a pretty common stripe size. And you want to spread that across 8 OSTs. So your file will end up being 1024 objects, and then you'll assign 128 of those objects to each of your selected OSTs. And those OSTs are typically spread across different servers, depending on how the file system is managed. And typically, it does a round robin. So the first block goes to one OST, second block goes to a different OST, and so you're round robbing across OSTs before coming back and hitting the first one you touched. Both of these parameters are actually under user control. There are defaults for the system, but for a particular directory, or so that when you set it on a directory, it affects all files that are created in that directory. Or you can say, for this particular file, I want to set these parameters. And this matters if you have large parallel data files versus small, like configuration files. You probably want to use different configurations for both. Now, facilities are doing their best to set reasonable defaults, but use cases and application logic are highly variable. And small files, you probably don't need to set anything, but if you have large files and you want to do fine-grained control of how they are laid out in storage, you might want to think about these parameters. So in the past few years, probably the past 8 years, I guess, Lustre's been trying to make life easier for both users and administrators. So one of the things is, for users, turns out people use lots of small files. We talk about HPC storage and parallel file systems, and we have so much capacity. The spread of small files versus large files on our systems is something like 90% are what we would consider small. Maybe 10% of the files are large, where large is like anything over a gigabyte. So one of the things that Lustre has implemented is the ability to actually, for small files, you can take your data and store them with the metadata. So we use up some extra space on our metadata servers inside the metadata targets. And so basically, when you ask for data from a file that's small, it can actually prefetch that data and return it to you with your metadata request, so that you don't have a separate I/O interaction to talk to an object storage server later on. Another thing is, when Lustre was first designed, you basically had a single metadata server per file system, and scaling the file system namespace was hard. They added distributed namespace extension, DNE. So this allows you to use more than one metadata target to manage directories in a single file system. That was phase 1, DNE 1. Or you can actually, for directories that have lots and lots of file entries, so this is process per file on large parallel jobs, you can actually stripe portions of those entries across multiple metadata targets, and this is DNE phase 2. Another one, I was happy to be part of the initial testing of this, progressive file layouts. So basically, those parameters that I told you about, stripe size and stripe width, they're set per file, but they apply to all of the file's contents. And that may not be good for certain use cases, but a progressive file layout is a form of layout where you can specify regions of a file that have different parameters. So for example, you can modify the stripe size or width for regions. And here I give an example of, you might want to use small stripe sizes for example, like the first megabyte of a file. And this will cover a lot of those small file cases, and you're not wasting a bunch of space. And then as you scale the size of the file up, so maybe you move up to 1 megabyte stripes for then up to a gigabyte. And then past that, you may want to use even larger stripes. This gives you the ability to customize the layout within a file. And then self-extending layouts are something that's been extended onto PFL. It's mostly to avoid out-of-space conditions. There's weird scenarios where progressive file layouts can be problematic, and you don't want to run out of space. So to talk about Orion, which is our next center-wide shared file system at OLCF, the interesting bit is the tiering, first of all. So inside the Lustre file system, there are two tiers. There are the capacity tier and the performance tier. So capacity, nearly 680 petabytes of storage, consisting of over 47,000 hard disks. You can see that the hero numbers for read-write bandwidth are roughly double that of Alpine. The performance tier is all NVMe SSD drives. So there's 5,400 of those, constituting 11.5 petabytes of space. You don't really need to know about this DRAID. If you're interested, there's number of parity, number of data disk, and number of spares is with the colons. And inside the metadata servers, we have 10 petabytes of NVMe storage as well, consisting of 480 of those spread across 40 metadata servers. So we have a single metadata target that's managing a pool of these NVMs. So we have 450 object storage servers. Each one of those has a 2 hard drive-based object storage targets and 1 flash-based or NVM-based object storage target. And it takes 160 routers. So these are the I/O nodes that route from your compute network to your I/O network. That go from Frontier into the storage IB network. So let's see if I can. So yeah, this is just racks and racks of storage, similar to Alpine, and then this is kind of the front view of some of these wraps. So all of these are, for example, just enclosures full of disks, the hard drives. And then up here are essentially nodes that run the object storage server logic. And we have routers somewhere over here. It's hard to read this picture. But so each one of these rows here is basically one of these whole. It takes a lot of space to hold that many disks. Anyway, so what's interesting about Orion? So it makes extensive use of these new Lustre features that I talked about. So it has the performance tier. So the plan is to treat this as a write-back cache. Lustre supports something called a policy engine, which controls how data moves within the tiers. And we're going to, plan a record, go with what HPE Cray is developing for managing the tiers. Although we're hedging our bets, and because we like to do storage stuff, we're also implementing and testing our own. We will use progressive file layouts, and it will be set up to, by default, write to the performance tier for the data. And then we'll take advantage of the self-extending layouts to protect us from running out of space in case too many people are writing at once. And we're going to try to stripe things such that, roughly the first megabyte, if you have something under a megabyte, your data is going to be stored on the metadata targets. So, and then the next few megabytes, we'll keep it on the performance tier and never stage it out. And then everything else will eventually, after time, be migrated to the capacity tier. And the expectation is you're not going to get read performance out of the performance tier. You're going to get read performance from what the capacity tier provides. And with that, I'll take questions.
I don't have any questions, but I'm really happy to see more progressive file layout for Lustre. So many, I've been doing this forever. And I can't count the number of times I've done, what am I getting bad performance? Oh, my stripe count is 1. Oh, all right. So you say facilities have different defaults. But sorry, nurse defaults are totally different use cases too. So one makes sense for them. Not for me, but for them it makes perfect sense. But I always forget. And, so I'm happy to see it will be a problem.
Oh, there's one up there too. Go ahead.
I'm not sure precisely when to ask this, but you mentioned vendors, so here we go. How do you manage, the kind of relationship with vendors where they have they're trying to sort of accomplish a different goal than us. So a contract with a vendor, the benchmarks and how you achieve the service level agreement or not, how you measure it or how they measure it. They want to make it maybe, or at least they have a financial incentive to not measure things, or make it harder to measure things or harder to complain even.
So I can only speak from OLCF's perspective, but the way we do that is, we have things that we tell the vendor they need to strive to get to. That's part of the contract for building the system, essentially. And then during that process, we have a contractual milestone that says, hey, at some point we're going to come up with a plan on how we're going to evaluate the vendor on these different characteristics. And so that's a negotiation between the vendor and us, saying, we plan to do these things, to measure these things, to verify that you're providing what you said you would verify. And the vendor can come back and say, no, we don't like how you're doing this. And so it's a negotiation. It's part of and eventually we all have to come to an agreement about, here's how we're going to verify that you're providing what you say you're going to provide. That's a high level description of how we manage that. But a lot of our leadership HPC systems are very, very complex beasts. And we actually have to pay the vendors a lot of money to implement things that they weren't planning to do. Sometimes those things work, sometimes those things don't work. And so there's also a lot of change management and project management and stuff that goes on, and you do your best to try to get your best solution. But
is there so you gave a high level example there, but is there maybe like your best, more technical in-depth example of just a useful benchmark or something you found useful to push?
So I can talk about our OLCF's acceptance process in general. So, and this occurs for both the compute system and the storage system. We have different acceptance plans for those two pieces. So basically, that includes functionality testing, which is making sure bits of the system function as expected. So, and this is like things like measuring raw feeds and speeds of memory, compute, et cetera, and making sure that basic software works. This is not like scale testing or anything like this. So we have functionality. Then we have performance, which is the performance of the system as a whole. So we take applications that we have done a lot of work to make sure that they actually run on the system beforehand and use them to evaluate the overall performance of the system. And then we have a stability test, which is basically a 2-week period where we run a full production workload mix of user interactions, compiles, jobs, et cetera, large set of applications and different programming models, et cetera. And the system has to, stay alive for that whole 2 weeks so that we can say this is going to be a useful production resource. And if something fails horribly in that middle of the 2 weeks, the time period starts over. And vendors are very motivated because they don't get paid until we say it's a good system. So.
Okay, thanks.
Yeah.
Quick question I had, just to be sure that in the Orion system, users won't see the performance and capacity tier like they just.
They won't have direct management over it, yeah. So you can still play with your own file layouts to try to influence, but the policy engine kind of, might, it's unclear to me at this point whether the policy engine will always override user set specifications or the user set specifications will override the policy, but I don't think we want to actually give users too much control, because then everyone will say, oh, I'm going to put all my data on the performance tier. So, that's not good for other users.
Scott had a quick question. Is Crusher going to be hooked up to Orion at some point or no?
So Orion is still very much in the functionality portion of acceptance. We are doing the compute acceptance now. After that point, we will hook up Orion to Frontier, and because we need Frontier to drive the performance testing of Orion. At that point, Crusher may be attached to Orion. I can't guarantee that will happen because I don't know for sure. So for those of you who don't know, Crusher is our small number of cabinets that look identical to Frontier that lots of ECP and early access people have had to play around with Frontier hardware. Yeah.
For the PFL, do users have to set up the regions, like define the regions, or
So
is like default?
That's the idea. So basically, the commands that you use to set those two parameters, stripe size and stripe width, you use similar commands to set a progressive layout. But the policy that I talked about for how we're going to place data of a certain size on the metadata and in the performance tier and on the capacity tier, so that's essentially a system-wide default progressive layout.
Okay, like how about, so like per file, the default one will be the 16 kilobytes for first 0 to 1 megabytes, that thing, or?
No, so it'll be this right here.
So, I mean, I think it's 2 slides before this.
So that that one was I was just giving an example of a progressive layout. Not this is not a something.
So per file, there's no default for that?
So no, it is. So basically, there are defaults for stripe size and stripe width on a Lustre file system, and that typically applies from the root of the namespace down. And then you can set it on a per directory or per file. But for Orion, the default layout is going to be progressive. And aligned with this placement. I don't know what the actual sizes, I mean, this just tells you the region's sizes, essentially. So up to a megabyte, we'll have some stripe size that plays nicely with the metadata targets. And then, the next couple of megabytes will play nicely with the flash tier or the performance tier. And then after that, you'll have some default stripe size that works well with the capacity tier. And they will document what those are. And if you need to change it, you can.
So size here basically means the stripe size, not the total file size, right?
Yeah, well, this is the regions of the file. So
Yeah, like the first 1 megabytes will go to the metadata part. And, okay.
So here, if it wasn't clear, these things are extent offsets essentially. So from offset 0, the file up to a megabyte, for example, would be on the metadata. And then the next region of the file up to a gigabyte would be on, but obviously those numbers don't match. Thank you.